Duane and Ruth are geology professors teaching geology together, but and they retired from that to teach geology at Acadia Senior College, which is where I encountered them, and many of some of you others have too. They are just amazing. If you take one of their courses, they will take you over hill and dale and in the back of people's property that you've never heard of before, and looking at all the crazy formations on MDI, which is what we got to see. And now they're going to arrive at Schoodic, where we'll finally find out what's happening on our side of the bay. So I think you're really going to enjoy the talk from Duane and Ruth Braun, and here they are.
All righty. Thank you. Can you hear me in the back? Yes. Okay? Okay. Always the first thing to check with this crowd. All righty. Ruth and I are semi-retired, and we like to say. We taught geology in northeastern Pennsylvania for 34 years, and then we moved up here. And we arrived here and discovered that we needed to keep doing some geology. So primarily I've been mapping for the Maine Geologic Survey, MDI, and then more recently Schoodic. And along the way, the park wanted us to write a book on the history of the park, so there we are. Okay, so let's get to where we are now, hanging out in Prospect Harbor on the Schoodic Peninsula, and good old MDI over here and Frenchman's Bay in between. So in this talk, we will be talking quite a bit about MDI, but then get on to Schoodic. And there we go. So geologic evolution of Schoodic and MDI. First, I'll be talking about the big picture over long periods of time, global and regional tectonics or mountain building, and finally glaciation. Ruth will pick up on MDI, the details of MDI, because that's where we have the best evidence, the best outcrops. And then I'll come back on to Schoodic, where we think it's the same situation as MDI, except that most of the good evidence is on the water. That's good. Okay? Okay. Yeah, let's keep going here. First, the big picture, plate tectonics, as we like to call it nowadays, or mountain building processes. Here we're looking at the side view from the Earth's surface down into the mantle. It's a cartoon, but still it tells a story. The big picture over time is that we have circulation in the mantle. Circulation in the mantle that is dragging plates of the crust, mostly sideways, across the Earth's surface. And the big picture over time is that the relatively thin, dense ocean crust gets subducted back into the mantle. That's the big recycling project on Earth. The continents, the crust under the continents is thick but less dense. They're like king-size geologic corks that float high on the mantle. So the continents are corks, the ocean basin is the dense, heavy crust, and that's what is generally recycled over time geologically. What we're looking at this point in this cartoon is 480 million years ago, when North America had just had a collision with a line of volcanoes, and we on the Gander train, MDI and Schoodic over here, are heading for North America. And we're going to close off this ocean basin. The big thing to remember about this is that over geologic time scales, tens to hundreds of millions of years, typically hundreds, ocean basins open and close. The Atlantic is opening today, the Pacific is closing. Ocean basin, continents break apart and reassemble. We have broken apart from a big supercontinent we call Pangea a couple of million years ago. Look at the globe, we're assembling another supercontinent in the northern hemisphere of the Earth. So this is the grand, big, long picture in geology. Now, North America. The old part of North America, the interior of North America, we geologists date at 1 billion years or older for the most part. The rocks there. The dashed line you see on this is the edge of North America 500 million years ago, or half a billion, if you like. Maine did not exist at that time. We weren't there yet. You see these colored stripes going down along the eastern shore of the United States today. Those are the strips of continental crust we geologists like to call terrains. They're added over 120 million years of time to build what is now the eastern part of North America and Maine. Let's look a little closer at New England. Here's that old part of the continent, Quebec up here. The green stripe is the line of volcanoes, what we call a volcanic island arc, like we see in the western Pacific Ocean today, collided with North America in about 480 million years. So the action was up here in northwesternmost Maine on down into Vermont, into the Cadillac Mountains down here. That's where the name comes from. So the mountain building was going on in northwesternmost Maine at 480 million years. This strip, we call a gander train, was arriving at 450 million. And so the mountain building was still in northwesternmost Maine, and we were on the trailing or quiet edge of the gander terrain. Then, at 420 million years, Avalon train rolls in, and that is when this whole area here, coincidentally, that boundary was parallel to the present coast. And if you stand on Cadillac Mountain, that's the horizon out there in the Gulf of Maine. That's where the boundary was between the two plates. And that was providing, that collision was providing the energy to have a line of volcanoes from Vinyl Haven to Eastport, 8 volcanoes erupting over the same geologic period of a few million years, with 2 of the biggest being MDI and Schoodic, sister volcanoes at the time. And then at 370 million years, Magma comes in, that's Nova Scotia basically, and that causes some other intrusion of igneous material here in MDI and the Gouldsboro Hills north of here. And then finally, the rest of the southern continent of Gondwana, the African part, arrives to collide with North America, 300 million to make the supercontinent of Pangaea. The big picture. And at that point, this is a high mountain range like the present-day Himalaya. The Himalayas from India colliding with Asia. This is Gondwana colliding with North America, throwing up a very high mountain range. We were kind of on the northwest flank of that very large mountain range at that time. Let's look at this time-wise again. Here is the overall length of geologic time, 4.5 billion years. Most of the action is going to be taking place in the last half billion, and we expand that into 3 different eras, Paleozoic, Mesozoic, and Cenozoic. We won't worry about all this other stuff for your purposes. So we're part of Gander. Gander is attached to that southern continent, Gondwana at that time, the part that is now South America. The rocks best match with the area in present day Venezuela. At 550 million years, we are opening an ocean basin and we're moving away from North America, the Gander train. Then we split off of the southern continent of Gondwana and start moving towards North America at about 520 million years. 450, as I noted before, we collide with North America to form the rest of Maine. 420, Avalon comes in and volcanic activity here, right near the plate boundary, right near the collision zone. And some other activity there, 370 on MDI and north of here in the Gouldsboro Hills. And then at 300 million, the rest of Gondwana comes plowing in to really throw up the Himalaya-like ancestral Appalachians. 200 million, things break apart again, close to where they came together. So we did leave a big piece of Gondwana behind. That's all of Florida. The fossils in Florida are African fossils, not North American fossils. The oil industry in the 1950s discovered that. They were baffled about when they drilled the first wells in Florida, the fossils didn't look like anything like North American fossils. And the guys from Africa said, oh, those are ours. Atlantic is opening to present. We are opening at about 2 to 3 inches a year, and we can measure that with military-grade GPS today, literally, year by year, the opening. And then, most recently, we've had some global glaciation over the last 2.5 million years to help sculpt the present landscape. Okay, that's going through time. Let's do some paleogeography just for fun. So here we are, a billion years ago. We had another supercontinent we geologists call Rodinia, a billion years ago. Most of the land masses were together. We got Q here for Quebec. We geologists call the old part of North America Laurentia. And here we are, G for Gander. There we are. And there's the South Pole. Here's the equator at that time. Basically, what's going to happen is that over 450 million years, this whole landmass is going to hang together and then rotate down to be centered on the South Pole. That's what this next picture is. Moving up 450 million years, here's the supercontinent starting to break apart. I mentioned before, Iapetus Ocean is opening. North America is starting its journey northward as it's continuing, and northwesterly. And the Gondwana mass, with us included, is just rotating in place. This mass of continents is going to hang around the South Pole for quite a long time, rotating in place. Let's move up another 50 million years, and now Laurentia. This is supposed to represent Greenland, Hudson's Bay, giving you a feeling for the orientation of Laurentia at that time. Equator. We're at the equator at this time, or at least northern Canada today is at the equator. And the green stripe, tectonic island arc, volcanoes are colliding with North America, getting ready to collide with North America. We are peeling off of Gondwana, South American part at that time, and getting ready to head towards North America. But we're down close to the South Pole at that time. We get that information from paleomagnetic pole directions that are locked in magnetic minerals in the rock. The magnetic minerals in the rock are giving us the compass orientation at the time. Moving up another 80 million years, Gondwana has collided. Our Avalon is colliding with us, and so this is when we are of a volcanic zone in the collision zone itself. But we're still near the equator, a bit south of the equator. We're in the tropical wet zone at this time. No trees yet, but it's tropical wet zone. So the landscape looked like this as it eroded for a long period of time. V-shaped valleys cut by streams with V-shaped ridges in between. This is the present Smokies. So this is what this area looked like for quite a while, though it eroded down to a gentler angle than that by the time glaciers arrived. The key thing to note with a landscape like this cut by rivers, no lakes. Okay, lakes are strange things. Glaciers really do a good job of scouring out lake basins. We should be thankful for that, at least on MDI, because An island in the Caribbean the size of MDI has big water problems, providing water for their people. Here in MDI and here in Schoodic, we have lakes, natural reservoirs. So that's why we can have 100,000 visitors today in August. But anyways, let's finish off with some basics on glaciation. Here's a cartoon of this region 25,000 years ago when we were covered by 5,000 feet of ice. Here we are in MDI and Schoodic on the Maine coast. The last glacier got down to the north side of George's Bank and on down to Long Island. George's Bank was dry land. It was a graded outwash plain, gravel plain going away from the glacier because sea level was down almost negative 400 feet. Why? Because all the seawater was in this glacier and several other glaciers around the world. But the Laurentide ice sheet in North America, actually, when it's down all the way here, is larger than the present ice sheet in Antarctica. Now, when the ice is down here, it's 200 miles south of us here. At that time, there's 5,000 feet of ice over our heads. Now, ice is 1/3 as dense as granite. So that's like putting 1,500 feet of granite over our heads. It's a lot of pressure. And as the ice was flowing over this landscape, rocks embedded in it were grinding away at our landscape. Out in the Gulf of Maine, these pink areas, those are big, broad basins scoured by the ice out of the softer rock out in the Gulf of Maine. Now, at 20,000, I started retreating back north, got to here around 15,000 years ago. And so we had going from 5,000 feet of ice to 0 here at 15,000 years ago. Should mention the ice first advanced across this area, we think, at about 35,000 years ago. So we had probably on the order of 15,000 feet of ice, 15,000 years of ice cover here. But you also have to remember, I spent most of my career mapping glacial deposits in Pennsylvania. There, we found we had 5 different glacial advances getting Pennsylvania. They certainly came across MDI. So the landscape you see today was sculpted by at least 5 glaciations, not just one. So it's a composite of the erosion effects of all those different glacial events. Some of the landforms, typically gently sloped hills in the north, steep sloped on the south, though some of them were that way prior to glaciation. We won't go off on that side tangent. But anyways, these Roches Mountainais, French term for an asymmetric hill. Then we have these deep glacial troughs with our lakes in them. The valleys were carved much deeper than the adjacent mountainsides by the flowing ice, grinding through things, carrying rocks at the base of the ice. Okay, Ruth, pick it up with the volcano.
Okay, before we actually go to MDI and Schoodic, let's review some types of volcanoes. Most people, when they think of a volcano, they think of a composite volcano. This is what you see out in the Pacific Northwest. Mount St. Helens, Mount Rainier, a lot of your others. These are a cone shape, fairly steep slopes here, and you have alternating eruptions of ash and lava. You can also have a shield volcano. Just remember that this magma is a little bit thicker. When it comes out, it's going to make these steeper slopes, because if you take a look at a shield volcano, like what you see in the Hawaiian Islands, this magma coming up is very hot, it's fluid, it doesn't trap gases, so when it comes up and onto the surface, you get a fairly low profile of materials, gently sloping sides, and it's basically all lava flows. Then you come to a caldera. A caldera has gently sloping sides let's take a look at what actually happens in a caldera. Calderas are found where the magma that's coming up is usually granitic. Granitic magmas are much thicker, they're cooler, they trap gases. And you know what happens when you trap a gas, okay? It's going to start to expand. And so as this magma comes in, if it gets a sudden heating, and we'll see how it can get this sudden heating, the magma chamber expands, and it literally fractures all the rock around it. If you then have an eruption, what have you done? You reduce the pressure. And since you reduce the pressure, you've got all this fractured rock. That fractured rock is going to sink into the magma chamber. These give you the very violent eruptions because of the trapped gas. What you have left is a caldera. It's bigger than a crater. It's a large area. You've got a flat area in the middle. You've got a rim around here that's fairly steep, but the outer slopes are fairly gentle. This is the actual caldera in the Long Valley out in California today. This is a very young one. This is still active. But this is very much what MDI would have looked like, and we're assuming Schoodic, and we'll see why we assume Schoodic. You had this caldera rim around a fairly flat area, and this is what MDI would have looked like 420 million years ago after the catastrophic eruption. So let's take a look at MDI. And why are we going to look at MDI? Because we have evidence on MDI. Okay, unfortunately, we'll see why we probably don't have as much on Schoodic, but we do have a lot of evidence on MDI. If you take a look at the rock units, you have the Ellsworth schist over here on the north side of the island. The Ellsworth schist is underneath everything here. It's underneath you two down here. Okay, we have Ellsworth schist everywhere. On the east side of the island, you get the Bar Harbor. The Bar Harbor goes under Frenchman's Bay and comes on and is up under here also. And then you have all these magma intrusions. So the first intrusion that came in was the Southwest Harbor granite. What's left of it is down here. Originally, you had a large magma chamber here and a large surface expression of it. This is all that's left. Other magma intrusions that come in are going to push this up so it's eroded away. Now I'm having trouble with my voice. Originally, MDI was not thought to be a volcano. Okay, geologists that looked at this looked at the rocks that were here and basically said, oh, these are a magma chamber. It has very large crystals that crystallize well underground. Down south here, we have something called the Cranberry Island series. The Cranberry Island volcanics, oops, too far, are down here. These are 10,000 feet of extrusions from a volcano. And it was always assumed that this volcano had nothing to do with the rest of MDI. Okay, it just sort of happened. It wasn't until this was dated, the Cranberry Islands were dated, they matched the Southwest Harbor granite, and in the early 90s, they actually matched it geochemically. Okay, you can take a look at the minerals and the material that's in the Southwest Harbor granite, and you can match it with the Cranberry Island series, which tells us one important thing. The Cranberry Island sequence is from an extrusive volcano, i.e. it erupted on the surface. When you match it with the Southwest Harbor, okay, I'm sorry. When you measure the southwest harbor, it tells us that the southwest harbor, which was originally thought to be just the magma chamber that never reached the surface, since you had these extrusions, it tells us that this was an actual surface volcano. When you take a look at the Cranberry Island series, you can go out to the Cranberries if you want to, or you can go over on MDI and go to the Seawall Complex. If you go to if you go to Seawall, you will see materials like this. This is what is called a pyroclastic breccia. These are fragments of materials that were torn up off the side of the uprising magma. It tore off pieces, it came up as an eruptive sequence, and it's surrounded by ash. And this stuff rolls down the mountainside very, very rapidly and then solidifies. So what we know now, this is a cross-section again, this is the surface, this is what's going on underneath. Here's the southwest harbor granite coming in. It's come through the Ellsworth schist. Okay, I told you the Ellsworth schist was underlying all this. It's come up past some of the Bar Harbor sediments up through. And it's actually a surface volcano because we know from the Cranberry Island volcanics that it actually reached the surface. It wasn't just the magma chamber. Then we're going to have a second intrusion, the Cadillac Mountain granite. Here's the southwest. Here's the Cadillac Mountain granite come in. Right here, we're just showing it as a magma chamber. This is what original geologists thought. They thought it never reached the surface. Into that magma chamber, we're going to inject some gabbro and diorite. This is very hot material. It's hotter than the granite. And, you know, geologists learn things too. We always assumed that when you had two magmas coming in contact with each other, you just sort of mixed. Okay, you dissolved a little bit of this and a little bit of that into the thing, but you assume you ended up with sort of a mixture of the two granites. We now know that when you have two granites and they vary in viscosity, how thick they are, how hot they are, they don't mix, they mingle. Okay, so we have magma mingling. Yeah, that's right, lava lamps. Okay, you have the two different types of material, and you remember that, you know, they don't mix, they mingle. And that's what's happening to the volcanoes here, is this dark material is coming up. This is the hot stuff, this is really hot. And it comes up, it tries to go through the granite above it, okay, in this sense, Cadillac Mountain granite. It can't do it, okay, it can't make it up through there. So it spreads out in sort of semi-horizontal layers. They give us these sort of, let's call them pillars. This is the diorite gabbro. This is the Cadillac Mountain. And you get these mingling. So Schoodic has several of these. They're not as good as the ones on MDI, and for MDI, so close. MDI is better.
Oh, those are fighting words.
So here's the Cadillac. Here's the magma that's coming into it, the gabbro. Remember, this stuff is very hot. Now, what happens when you put something very hot in a closed container? It expands. Okay, you got extra energy. So this whole magma chamber is going to expand. And as it expands, we're going to find around the edges, and we have them preserved still here on MDI, of what we call the Shatter Zone. Okay, as you put this hot magma into another magma chamber, you overpressurize the magma, and you end up shattering the rock around it. That shattered rock will then be incorporated into the magma around it. And the shatter zone, this is what you can see on MDI. It's not quite so evident on Schoodic. This is a big piece of Bar Harbor. This gray stuff is the Cadillac Mountain, and the darker ones are some other basaltic material. But this is all incorporated into that shatter zone. And to give you an idea of what's happening then, here's the Cadillac Mountain. Here's that gabbro that comes in. That gabbro overpressurizes that chamber. Okay, you're adding a lot of pressure. It fractures the rock around it. That rock then sinks into the magma chamber below. And so you have formed the shatter zone. Now, this happened 420 million years ago. Okay, so most of that land surface has been eroded. This is what you see today. Okay, and that's why a lot of original geologists, some of the first geologists, took a look at this stuff and said, oh, there's big crystals in these magma chambers, therefore that had to have crystallized well below the surface, and therefore there was never a volcano here. It wasn't until we matched up the Southwest Harbor granite with the Cranberry Islands that we realized that, number one, 420 million years, you've got a long time to erode things. You can remove a heck of a lot of material. And I guess I will turn it over to Duane.
George Schoodic. Yeah. Go back to this thing, though. Think about this. I mentioned about the ancestral Appalachians. So we have this huge mountain range, uplifted and crumpled up and such. So while that was crumpling up, so also that's why things are tilted in various ways here today. It's all this crumpling going off to our southeast out there towards what is now the edge of the continent. And so this area has been greatly uplifted, greatly tilted, and erosion has been chewing into here for a long time. So this is the present landscape. Blue Hill Bay, Frenchman Bay, MDI, Schoodic off the diagram, this diagram. Let's go take a look at both places at the same time. Complicated diagram. This is just a snapshot of a piece of the state of Maine geologic map. But the key thing is that here's Schoodic here, where we're right there, and MDI. So we are two big masses of igneous rock that was intruded into the crust and then extruded as volcanic activity. The radiometric dates are the same for Schoodic and MDI, so we were erupting during the same million years, so to speak. Just a brief time for us geologists. And then don't go there yet, Duane. Ellsworth schist, as we mentioned, that's that older stuff, that 500 million year plus stuff, metamorphic rock. That's underneath everything here, pops up here, pops up there. And then the Bar Harbor sediments that are out in Frenchman's Bay and around in the Blue Hill Bay, and we think offshore here in a few places, and up a little bit north, that's on top of the magma that's being pushed up. And then we have the two igneous centers themselves. Here we are in on Schoodic. This is just a black and white aerial photograph of the area. And let's find ourselves again. Here's Gouldsboro up here with Route 1, right up in this area. Coming down into Winter Harbor and over to Prospect Harbor here and down at the point. And so the game here in Schoodic is that we have this darker igneous rock that we call gabbro and diorite up in the northern area around Route 1 in Gouldsboro. Then we have a granite unit here coming on south of that, my G1. That's granite with these black blobs of basalt in it, a diffuse mingle. And then we had coming on down into this area, Prospect Harbor and such, and close to Winter Harbor, we have this light pink granite that has a lot of light pink stripes in it. Those are the felsic dike. felsic is a fancy word for fine-grained granite. And then from Winter Harbor on down past the Schoodic Point area, this is basically the park area, we have another granite that's very much like G2, but it does also have some dark blobs, and it actually has some zones of quite a few of those mingling blobs in a couple areas down towards the point. Now, the main problem with Schoodic is that the edge of the magma chamber is out here in Frenchman's Bay. It only comes ashore just briefly on the east side of Ironbound, and then we just catch Grindstone Neck for a little, about 100 yards of shoreline, and it goes back offshore here. So, but the stuff here and here is Shatter Zone. So we have at least a little bit of the evidence of some very violent things going on here at Schoodic, just like on MDI. We have no volcanic rock because if there is any reserved, it's out under the ocean. Kind of stuck here. Now, the other northern edge of the magma chamber is up here. And what do you got up there? You got a lot of spruce trees. Okay? And it's really hard to see much of anything up in that neck of the woods. So evidence of this being a volcano is minimal, but we have a little bit. And it's the same age, same kinds of rocks, basically, as at MDI, so it makes sense that's a volcano. And also several other places along the coast here, Vinyl Haven, Eastport, we have a lot of other volcanic rocks with these magma intrusions of the same age. So again, really a safe assumption, if you like, that this also was a major volcano along the line of volcanoes from Eastport to Vinyl Haven. Let's take a look at the side view. We're going to draw a trench, so to speak, north to south across Schoodic. And so we have another one of these side view or cross-section cartoons. These are not the formal cross-section, but simplified. We are lying to somewhat. We're simplifying the story. Okay, there's a lot of other little details that we're glossing over, and things like that. But simplify matters. So here we are, we're just starting off with the Ellsworth shifts underneath here. And we got Bar Harbor and some other lava flows to the north. On top of the Ellsworth, then first comes in the dark, really hot gabbro material that starts things off just like an MDI. But we have surface exposures of that in MDI. We do not have it here, except for a little blob up here. Then we have the first granite coming in, that G1 on my map. And so that's starting to erupt, just like the Southwest Harbor granite on MDI. And so we are developing this caldera. Up around Route 1, we have this really wacky mix of mingly blobs and other stuff in between. And we assume there are some volcanics at the surface, but we have no present evidence of that. And then we bring in the other granites. This is an asymmetric system, the way it looks in the maps. It blobbed off to the south more than the north. It wasn't so symmetric like it was on MDI. But this is the cartoon version of what has happened here under the Schoodic area from north to south. And each granite comes in and kind of widens the caldera, we think. And we also deposit a lot of volcanic material up on top, a lot of shattered material on the caldera floor. And then towards the end of things, we have some other minor injections of material that give us all those dark stripes down on Schoodic Point and other places here on the peninsula. Now, today, that's what we got left. Okay, we've had a lot of erosion, and so we're deep in the guts of the magma chamber, so to speak. And so we're over here at Schoodic Point, a bunch of dikes cutting that granite, and Route 1 up here. And so we're just seeing the intrusive part of that overlying volcano. This is a field map of mine. I've been working on the part of the Schoodic Peninsula, mapping out dike complexes. I only have 1,000 data points presently. I had 5,000 data points when I was working on MDI. And so I'm just tracing out many of the late stage intrusions of mostly that dark colored basalt across the granite. Got a blank area in here. Have you ever been in there? A lot of spruce trees. And that's about all you see, a lot of spruce trees. But anyways, detail down on the West Pond, as it's called. There's a lot of dikes cutting things down there, cutting each other down there. Things get kind of complicated. And that's also cutting some of that blobby mingle stuff overall. There's the strip of the blobby mingle stuff in the granite overall, and then all these dark dikes cut that. And this is a picture on shore, or looking towards that shoreline, and you can see all the different dikes. This dike itself is a mingle. It's blotchy colored. There's all kinds of dark basaltic blobs in with the granite coming up through. Another darker one, and this one's cutting this one. Anyways, a lot of stripes down there in that part of the crystallizing magma chamber. These dikes are cutting the crystallizing granite. There's still partly molten granite there. What we've found in the last 20 years through laboratory experiments that they actually do make magma and then crystallize it. Once the magma is 30% crystalline, the crystals start locking together. Once it's 50% crystals, they're really locking together, and then you can crack it. Once you can crack it, then you get these dikes coming up across it. When Ruth was talking about that mingle, that's when the granite is fully fluid, no crystals, that blocks this dark rock from coming up. Once it's a little bit rigid, partly crystalline, then you crack it and get these dikes coming across it. It was all news to us. We never heard of that stuff as undergraduates way back in the 60s. But anyways, let's hit the glacial stuff at the end here. Here's Maine, basically 14,000 years ago when the ice is up here. The weight of the glacier, remember, it's 5,000 feet of ice over MDI, but the ice edge is down at George's Bank. We had 5,000 feet of ice over our heads for at least 5,000 years. And that weight pushes down the crust. There's mantle material slowly oozing away from this glacier. So the crust is being depressed. And what happens when the glacier melts back through? It melts back through faster than the crust can come back up. And so the ocean actually floods into Maine. And so this is the maximum extent of the flooding of Maine at about 14,000 years ago. All of the central lowlands of Maine, up through Bangor, Orono, going all the way up to Medway, almost to Millinocket, was under the ocean. And here in MDI and Schoodic, just the highest parts were sticking up. And the ice was just north of this area at 15,000 years ago. We got good dates on that. Here's a sea level curve. Okay. Over here is elevation, present sea level, going up 200 feet, going down 200 feet. Here is time, present, going back to 16,000 here, 15, 14. At about 15,500, we have good evidence now that the mountains tops on MDI were just coming out of the ice. And the ice front was just pulling back beside the mountains of MDI. It was just north of much of Schoodic, heading towards the Gouldsboro Hills. And sea level at that time, we have this big delta built in the ocean at Jordan Pond House, and that's at 230 feet above present. So the crust was pushed down below the sea level at that time, 230 feet. And then what's going to happen, as I note over here, 10 to 15 feet of uplift of the crust, meaning sea level drop, over 100 years. If you were a Native American living around here at that time, we did have Native Americans at that time, you would, in your lifetime, see what was low tide become high tide, sea level dropping. And then things drop to present sea level about 13,000 years ago. Things would look like they do today, sea level rise, but then zoom, it just kept dropping to negative 190. There would be a little bit of water between Schoodic Point and Otter Point out in the center of the channel going to Frenchman's Bay, and then offshore further. And all the islands offshore would be hills on the mainland. Whoops, wrong way. Then sea level would start coming up quite rapidly. That's global sea level is rising. Our land level rise has slowed down and stopped pretty much around 10,000. But anyway, global sea level was rising rapidly as the glacier continued to melt. I should note that as land is rising here, the continental ice sheet has only lost about 5 to 10% of its mass. So global sea level is still way down there. Anyhow, we got global sea level rapidly rising for a few thousand years, levels off for a while, then goes back up again. Let's not worry about the details here. And the key thing, last 4,000 years, we've gone up one tide cycle. So 4,000 years ago, high tide is the low tide line. Okay, 4,000 years ago, low tide was high tide, all right? And MDI was still attached to the mainland. And, of course, things will be interesting in the next few hundred years. With also the tide gauges, if you could stick the last few decades of tide gauge records in, you see it ramping right up there. And so we geology types like to talk about the next several hundred years. We're really fully expecting sea levels to be 10 to even 20 feet higher in the next 300 years. We aren't going to get rid of much more CO2. We're probably going to keep adding for the next couple centuries. And so things are going to keep ramping up. Such is life. So here we are map-wise. When sea level was at plus 230 feet, the ice had just retreated north of here. MDI was a series of several islands, with the individual mountain peaks being individual islands. Schoodic, one little island. What's that? Schoodic Head, the only thing that stuck out of the water. The entire peninsula was underwater, all the way up to the Gouldsboro Hills. Also, it's a much more narrow peninsula than MDI. And also another, here it is, the negative 190 sea level. A little bit of water there between Schoodic Point and Otter Point. Narrow strip coming up towards Blue Hill Bay. Note these three blue spots. Those are freshwater lakes. Frenchman Lake, Soames Lake, and Blue Hill Lake. They were lakes for several hundred to several thousand years before sea level rose enough to flood back in to make them estuaries. And in places they have drilled them, and there are freshwater peaks underneath marine mud in those bays, once were lakes. Now let's take a look at Lower Schoodic, where the park is. North is this way on this image now, sideways so to speak. And what are you seeing? This is what we call a LiDAR image. This is from using a laser beam from an airplane to get you the land surface. And we geologists can, with that data set, remove the vegetation. This is bare ground image. We've gotten rid of the vegetation. Okay? We geologists like to do that. And You see the rough texture to things, that's essentially bare bedrock. That's most of the lower peninsula, it's just mostly bare bedrock. There's a little bit of beach cobble up where, that's the new campground area here. There's some beach cobble over here, a couple other little patches, but mostly it's bare bedrock. Schoodic head here, the only thing that was sticking out of the ocean initially as the ice retreated. And so we have a relatively narrow peninsula that was totally flooded by the ocean. The glacier also was retreating quite rapidly when it was retreating past Schoodic. And so it wasn't leaving much debris behind. And then we have the waves coming in, attacking the relatively narrow peninsula from both ways and stripping off what little glacial debris there was. So in one regard, that's why it's still pretty much undeveloped, right? Because we humans didn't have much use for it, for the most part. A little bit up here at Fraser Point and such, but really, we never had much use for the place. Now, inland a little bit, though, we have the glacier leaving a bunch of stuff north of Winter Harbor, Prospect Harbor, back towards the interior of the peninsula. We do have some interesting features. We call them a bunch of push moraines. And how you develop those things is that when the glaciers are retreating out of this area, kept emphasizing that the land was underwater, under the ocean, what we call a marine-based glacier. It's retreating mostly by calving off a bunch of icebergs, a big high ice cliff, as it's retreating out here, like you see in the bays in Alaska today or in Antarctica. And as the ice is flowing out of there, we're splitting it apart and sending it off. Underneath, we got meltwater coming out. It's carrying a lot of ground-up rock debris, so this is really muddy ocean water. I should have made it brown, I guess. And it's leaving us a layer of marine mud on the landscape. And if you ever see any farm fields in this region, that's marine mud. Not many rocks, marine mud. So there are a few, whoops, did I hit the wrong button again? Let's go back. There are a few drop zones, the chunks of rock that floated off in the iceberg and dropped down. If you ever take Mud Creek Road, heading over to MDI, right? You've done that. Well, Mud Creek's appropriately named. But look at those fields, big hay fields, right? Where are the rocks? Ain't no freaking rocks. Marine mud. Lots of marine mud. Those are wet fields of work, but no rocks. Anywho, now, I have a summertime picture of this glacier, actually, or early spring, really. And what's happening is that the ice is really breaking apart, starting to retreat. And this is the pile of stuff that was built up the previous winter. As the ice is retreating, it retreats primarily in the summer, and then each winter it stabilizes and then pushes back a little bit. It's like a big bulldozer. And so this is the previous winter's pile of stuff we call a moraine. That's that year's pile of stuff. And it's going to retreat back and build another one back here. I've mapped 300 of them from north to south across MDI. So that's what we see, these little piles of stuff in the interior of this northern part of the peninsula. This is the so-called LiDAR image of the area north of us here at Prospect Harbor and Winter Harbor. Look back inland, see all these little things? Okay, there's these little moraine ridges, a few hundred feet apart, 5, 10, 15 feet high, 50 feet or so wide. If you're standing on them, it's hard to see, especially standing in the trees. Okay, I can take you out there, and you're looking out there and saying, huh? I have a couple places I take people on MDI that actually are farm fields that, oh, yeah, they're there. Okay, but in the woods, forget it. But these are really like tree rings. They're marking the annual winter still stands, you might say, or pushbacks of the ice. And you can actually count these going back, so to speak. So that's the most interesting glacial feature on Schoodic, so to speak. Okay, a lot of these little push moraines back there in the interior of things where most people don't go, though just recently this area has become a conservation area. I should get back into. This has been logged in recent decades, and it's hard to get back into also. Okay, I've learned to honestly hate spruce forests, but anyway, trees down there. Okay. Enough is enough. Questions out there? Yes, over there.
So, because I do spend a lot of time up there by Forbes's Pond hiking all around
Yeah.
just to see if I get from here to there. Just to orient myself, so Forbes's Pond, and then you've got the ridges.
Just next to it there, the road is coming up, it's hard to see the road.
Yeah.
There's this little gravel pit there.
Okay, so is
It's
the,
coming up like that, the road.
but the ridges, so the ice was moving this
The
way.
ice is retreating that way.
That way.
Yep,
So the ridges
perpendicular.
are,
to the ridge.
yeah.
These are
Okay.
marking the edge of the glacier.
Okay, so not going this way, but actually going this.
Right, heading
Yes.
north to north and northwest. Right.
Coolio. Thanks.
Yep, another question out there. Yeah, over here.
That was actually my question, was that, so that's showing you the retreat direction of the glacier, which is, it's not, straight north, it's going northwest.
Yeah, the glacier always came from the north-northwest, going south, and retreated back to the north-northwest. Yep. Heading back to happy Quebec. Yes?
I just want to ask, with regard to recent events like the glacier, are we still rebounding here?
No. What we geologists call the hinge line and rebound is just north of the St. Lawrence River at the present time.
Okay, so then what is causing the
We have
in
tectonic.
sea level, I guess that would
Well, we have, of course, the global sea level rise thanks to the whole CO2 thing. But here on the coast of Maine, we actually have some other, we don't know why, but parts of the Maine coast are still gradually going up and going down. We have a downer between here and Eastport at the present time, going down a few millimeters a year.
so it's depressing slightly.
Depressing, right? It's a regional depression. We don't know why per se, but all across the continent of North America, now with very precise leveling, we see that areas are going up and down very gradually. And the thing to think about is that there's mantle material always moving underneath us. Okay, centimeters per year scale. But so that's always deforming, putting energy into the crust. And so there's always regional wrinkles, if you like, in the crust from the mantle material moving underneath.
So what would be your estimate of when the next ice age will start and we're getting the glacier coming south?
Okay, that's a good one. We have found that certainly in Milankovitch cycles, solar cycles, or in other words, our orbit around the sun has a particular pattern that changes systematically through time. More elliptical, less elliptical, a tilt of our axis a little bit less, a little bit more. So we can calculate, back calculate, and forward calculate what we expect the solar energy input, i.e. the overall temperature to be, and that is what really matches our previous ice ages very well. We can calculate it millions of years in the future. The next cooler period we expect to be starting soon, but will not be anywhere near as severe as the last one. And we humans, we think, may be able to defeat it. Keep pumping in CO2 for a while longer, and we think we may be able to defeat the next ice age. The Canadians like that.
Is that good or bad?
Well, if you own coastal property, get your butt in. Anyway, all right. If we melted all ice on Earth just for kicks, okay, we would end up at 230-foot sea level elevation, right where we were 15,000 years ago. I get a kick out of that one. When you do the calculations, all the ice in Greenland and Antarctica, you melt all that stuff, you end up with sea level 230 feet. We aren't talking about melting all of Antarctica. And all the stuff we've been talking about, climate change guy, we're going to melt a good part of Greenland, we're going to melt part of the West Antarctic sheet, a little bit of the East Antarctic sheet, and nobody's talking about melting the whole damn thing. We really don't want to see that, okay? Yeah.
In the days of Pangea, was all of the dry land on Earth on one corner of the globe?
Probably about 90%. There were a couple chunks floating around, but
All right, but most of it is on one side of the globe,
Right.
all right? Wouldn't that make the Earth?
Okay. Thank you for that question.
That's a great
I always want to do that one. Okay. So everybody, you see a classroom globe about this big? Okay. Then you got the crust, you got the mantle, and you got the core. Now, if you scale that properly, the crust is thinner than the paint on the globe.
Okay.
Okay? Crust is nothing. It's maybe 10 miles thick in the ocean at most, 25 miles thick. Okay? But they're thousands of miles thick. I always love these people like, oh, we're going to flip everything around because the crust has moved. Come on, guys, you're moving the paint in the damn globe. Hey. I like that. Thanks for that question. I always get to that. I'm going back here further. Back in the back. Yes.
I've been to Mount St. Helens shortly after it erupted, and I was just wondering, is that a caldera?
No, that's a composite volcano. That's a small hiccup. I'm sorry. Okay. That was nothing. Okay. MDI is considered one of the super volcanoes. MDI and Schoodic are about 1/4 the size of Yellowstone when they erupt. Okay, guys? You don't want to be around here at that time. All right? You're going to be incorporated in the ash beds. All right?
So when you talk about the Gouldsboro Hills, are
Yeah.
you talking about Top Mountain?
Schoodic Mountain Tunk.
Yeah.
Yep, black.
Is that part of the volcano?
No, that's another intrusion 50 million years later, 70 million years later. Okay? We have no evidence, but it's been eroded away, that ever reached the surface. Certainly was a major intrusion, really beautiful circular feature if you looked at my first diagram or slide there. And but we have no evidence that it ever reached the surface. Okay? In the back.
Any idea if land moves around on other planets like it does here?
We have no evidence of plate tectonics in our solar system, except for the ice planet, the ice moon of Jupiter, which I just forgot the main name of. No, Io is
Titan?
yeah, I think that's it, yep. So we have some ice planets, we think, around Jupiter, the moons, and it looks like they're having plate tectonics, but in ice. So that's the only evidence we have. Yes?
I have a couple questions. One is, have you looked at any of the silver mines in the Gouldsboro?
No, I haven't. Up Sullivan way. Yeah. Yep,
And
yep.
then,
They did actually produce some silver, yeah, for a while.
yeah, they did.
Yeah.
And the other question I have was, I find those blotchy rocks
Mm-hmm.
on the seawall just out in front of my house. So they have black
Blobs.
blobs.
Mhm.
Is that it's not the mingle, or is it the mix?
It probably is mingle if they're distinctly rounded or
Yeah, they tend to be round. But they look
that means that the stuff was molten
Yep.
in the other molten stuff. If it's rigid, it's going to have sharp edges.
Okay, and maybe just a throwback here, but I've seen volcano down in Guadalupe, and some of the Caribbean and Montserrat had
Mm-hmm.
huge eruption.
Mhm.
And in the St. John Virgin Islands, the
Yeah,
tectonic plates there.
Those are a whole bunch of composite volcanoes. Okay? And any eruption that we humans have had in recent decades is small potatoes.
Right, but when I was in St. John, it looked like some of the land mass there reminded me of
MDI.
the granite, yeah.
Yeah, right. There are some older areas there that have been uplifted and eroded into. You're actually getting into some magma chambers there, the upper parts of them. Yeah. The silver mine thing was interesting too, is that a lot of our gold and silver deposits out in the western United States, those are the squeezes, if you like, from a magma chamber. They're generally found rising through the rocks above the magma chamber. And here, we've already eroded just about all that stuff away. bottom area, okay, we're too deep for the most part. Now, the silver mine areas are some veins off to the side of one of these intrusions that still has some of the stuff that makes you a little money if you want to waste your money.
Did I hear correctly when I was at Niagara Falls, the American Falls, about 20 feet down, is Ellsworth schist?
No, no, it's all sedimentary rock in the falls, indeed. That's the Lockport dolomite on top, and there's some shale units underneath. It's what's undercutting it.
With all this volcanic action, where was Maine on the globe at the time that all of this?
Oh, remember that? The Paleogeography. Yeah. Okay, so here we are at 420 million years ago, when these places were volcanoes. Okay?
So we were right on the equator almost.
Just south. As I mentioned before, we're in the tropical wet zone. That's why in our book we have a lake in the caldera. Okay? But like Ruth likes to mention is that if you look at the land surface, like Long Valley caldera today in California, it's got trees in it. No trees. This is before trees evolved. We had moss, we didn't have trees yet. Okay? But, right, we are in the tropical wet zone at that time, a bit south of the equator. And we'll be drifting north across the equator as the rest of Gondwana comes in. Most of the Paleozoic, we're hanging around the equator. Yep.
Who comes up with these crazy names for these?
These are geographic features. Gondwana is a geographic feature in Africa. Okay. So we geologists always use the name where you first describe some feature. Okay, the Ellsworth schist is named because we first described it in Ellsworth. Okay. Laurentian Hills of Quebec. It's a geographic term. Okay. So those geographic terms are attached to the geologic feature that you find there. How we doing there? We're running out of time. We can go on all night. We got Geologic Time working for us.
Well, Rita, and thank you very much. This is a...
Oh, we got some books over there. If you want to buy one of our MDI books for $20, we got them over there. 100.